Hi, this is Dr. Bricker here with a review for Exam 3. Exam 3 will cover the following chapters and sections. So Chapter 7, Rotational Dynamics. Chapter 8, Static Equilibrium, so basically balancing forces and torques. Then we jumped up to Chapter 14, which is on oscillations, specifically simple harmonic motion and a mass on a spring. So sections 14.1 through 14.4. And then we did standing waves, waves on a string. So that's chapter 16, section 16.1 through 16.3. So again, waves on a string. Also fluids, and the sections of chapter 13 on fluids is 13.1 through 13.5. And then finally, chapter 12, thermal properties of matter, and 12.1 through 12.6. So if you look at it, 1, 2, 3, 4, 5, 6 chapters, but not all the material for each chapter. Chapter 7 and 8, we basically covered all of that, but simple harmonic motion, again, we stuck with a mass on a spring. Chapter 16, it was standing waves on a string. Mass on a spring, I should have said, and this is waves on a string. And then fluids, we didn't do anything with turbulent flow. We stuck with 13.1 through 13.5. And then thermal properties, again, not the complete chapter. So although there looks like there's a lot of chapters, we didn't do all the sections of those chapters. Now, if I were going to study for this, I would definitely go over the practice exam, look at the homework questions. Now, we didn't have a homework assignment for section 13.5 or chapter 12. So for that, make sure you look through the example problems in section 13.5, and then also look at the example problems given in chapter 12, section 12.1 through 12.6. And another thing I would do if I was studying, definitely reread the chapters. If you don't have time to go through all the chapters, at least read the summaries, take a look back through the videos. As far as a formula sheet goes, you just like before, 1 8.5 by 11 handwritten sheet, both sides, put whatever you want on there. The form of the test is the same as before. It's multiple choice, but you have to show your work to get full credit. The actual test has the same amount of questions as the practice test. Okay, so let's just go through this, and I'll work out these problems and give you some hints along the way. So the first one is we have a string that's 2 meters long. Okay, so the length is 2 meters. Fixed at both ends, as you see here, and tightened until we have a wave speed of 18 meters per second. What is the frequency of the wave shown? So how much is the frequency? Okay, so the first thing to figure out is what mode are we in. 1, 2, 3, 4, 5, 6 antinodes. So m is equal to 6. So the wavelength is given by 2L over m. So we can figure out the wavelength from that. Again, the wavelength isn't the length of the string, it's 2L over m. And then I can get the speed, because it's related to the frequency and the wavelength this way, so then I can solve for the frequency. The speed divided by the wavelength is equal to the frequency. So the speed's actually given here. The wavelength I've got to do a little bit of work for. Once I get that, I can get the frequency. Okay, excellent. So without putting in numbers, that's the way to get the answer here. So you'll see something definitely similar to that. And note, m is equal to 6. That's from the antinodes, the high spots here. Next one, we have a 1.5 kilogram air track cart. Okay, so mass 0.15 kilograms, attached to an ideal spring with a spring constant. Okay, so K is given, 3.58 newtons per meter. Undergoes simple harmonic motion. What is the period of the oscillations? So when it says simple harmonic motion, mass on a spring, immediately you know the relationship between period and the spring constant. So 2 pi square root of m over k. Now if you think about it, it's a mass on a spring oscillating back and forth. The speed keeps changing. The force keeps changing because the spring is compressed more at other points, compressed less at at different points. So it's really complicated to try to analyze the motion. You can't do it with kinematics because acceleration is not constant. But because it says simple harmonic motion, we have this for the period. You know m and you know k. Don't forget about the 2 pi. So it's sort of a plug and chug problem if you realize simple harmonic motion, which you should because it tells you it. If you're given the mass and the spring constant, then you could figure out the period. One other thing about this, so this solves this problem. For simple harmonic motion, there's a few other points we can talk about. The total mechanical energy, it's 1/2 Ka squared, and A is the amplitude. It's also equal to 1/2 mv max squared. And then, this is at the endpoints, plus A and minus A. This is where it passes through x is equal to 0. That's where we're going the fastest. And just at some general random other point, we would have 1/2 kx squared. That's the spring potential energy, plus 1/2 mv squared at that point. So if you're given the total amount of energy and the amplitude, you can figure out the spring constant. Or if you're given the total energy and the maximum speed, for example, you could figure out the mass. So this works perfectly well for us for this problem. Just keep in mind we have this energy consideration, so we can take a look at as well. So you'll see something similar to this problem as well. Okay, moving on to the next one. How much heat is required? So heat is Q. How much heat is required to raise the temperature of 225 gram, so 0.225 kilograms divided by 1,000, from an initial temperature of 15 degrees Celsius to a final temperature of 25 degrees Celsius. And we're told that the specific heat of lead is 128 joules per kilogram Kelvin. Now remember, 1 degree change in Celsius is the same thing as a 1 Kelvin change in temperature. So this is also equal to kilograms per degree Celsius. Okay, so the relationship between heat, mass, specific heat is this. Q is equal to mc times delta T. Okay, so we want to know how much heat is added. So heat's measured in joules. We can figure this out from this relationship. mc and the delta T would be the final temperature minus the initial temperature. And then we know everything. We're given the mass, actually. Just make sure you put it into the appropriate units. Given in grams, we need kilograms. C, specific heat, also given here, so we know that. And then we know the final temperature, 25. The initial temperature would be 15, so the change in temperature is 10 degrees Celsius. Good, so you can solve for it that way. So this comes from Chapter 12, and there's a lot of information in Chapter 12. So if you look at all of the practice tests, this was the only question from Chapter 12. So just to kind of narrow it down a little bit, I mean, you have a lot of information to study. Look at something like this problem, where you're looking at how much heat does it take to raise the temperature, or you could think of it about it like, given this much heat, what would the final temperature be? Something like that. So when you're studying Chapter 12, take a look at this sort of problem. I didn't put any phase change questions on there. It's something more similar to this. Okay, just a little hint for you. Okay, the fourth one, as shown in the figure, a given force is applied to a rod several different ways. In which case is the torque about the pivot point P due to this force the greatest? So torque is F perpendicular times R, or R perpendicular times F, or RF sine of the angle between those two. So this one here does not give us any torque. This would not make it rotate at all. Now if we compare 1 and 2, this force is applied at the end, this force is applied at the middle, so this is going to have twice as much torque as this one. So this was not the greatest. So this torque, this force, and this force are applied at some sort of angle. A little bit of an angle, a little bit of an angle. Whereas in the first one, it's completely perpendicular. So this will give you the biggest torque. Okay, and if it said explain, I would say number 1 is greatest torque because the force is applied perpendicular to R, where R is the greatest. It's the greatest, you know, compared to like number 2 here, for example. Okay, good. Going on in the 5th one. A large 75 kilogram lighting fixture can be hung from wires of identical size and shape and made of aluminum, brass, or copper. Okay, so we're hanging this mass from some different wires: aluminum, brass, copper, and the Young's modulus for each of these is given. So 0.7 to the 11th, 0.91 to the 11th, 1.1 for copper, also to the 11th. Which wire would stretch the least distance? So this question comes really from Chapter 8, the equilibrium and elasticity chapter. So for Young's modulus, we have this. The force is equal to Young's modulus, cross-sectional area, delta L over L. We had a couple of homework problems on this. So Y is Young's modulus. L is the actual length of the wire. This is the cross-sectional area. And then delta L is how much you actually stretch the wire. So you could think of this as being kind of like a spring. So the bigger Young's modulus, the stiffer the spring would be. The force in this problem is actually given by M times G. That's what's actually stretching the wire. So the one that will stretch the least distance, because the force is all going to be the same, the one that's going to stretch the least distance, so the one with the smaller delta L, would have the bigger Young's modulus, because the left-hand side of the equation is going to be the same. So this is what I'm trying to say. The force is mg y a delta L over L. So the one with the largest Young's modulus will have the smallest delta L. So if you go through here and you pick the one with the greatest Young's modulus, so the Young's modulus for copper is greater than for brass and all the other ones. So brass, and that's bigger than the Young's modulus also for aluminum. So this would stretch the least, this one would stretch the most. Okay, very good. So take a look back at this. Don't forget this equation for stretching a wire. Okay, number 6, we have a 4 kilogram cylinder of solid iron supported by a string while submerged in water. What is the tension in the string? Okay, so this is a fluids chapter problem, and there's an additional force on this shape. So it's being hung by a string, something like this. Now, if this were not in water, the tension would just be equal to mg. This is in water, so we also have a buoyant force up. This is just like one of the homework questions. So we've got buoyant force up, tension up, and we have mg down. So we know the mass, 4 kilograms. It's solid iron. We want to know what is the tension in the string. The density of iron, 7860 kilograms per cubic meter. So this is of iron. The density of water, it's given here, but we should probably know that one, 1,000 kilograms per cubic meter. Okay, so balancing forces, we have this. This really goes back to chapter 4. The new part is here, we've got this additional kind of force called the buoyant force. And then that's equal to m times g. And then we can solve for the tension. So mg minus the buoyant force. Okay, so if we know the mass, actually the mass is given, so that's easy for this one. The mass is given, I'll just write it one more time, mg. So we know m, we know g, minus the buoyant force. So this is the density of the fluid, volume of the fluid that's displaced, times g. That will give you the buoyant force. So the density of the fluid we know, it's water, so we know the density of the fluid. G we know, we know the density of the fluid, we know g. The volume of the fluid we can get because we know it's completely submerged. The volume of the fluid displaced is the same thing as the volume of the object because it's completely underwater. And then we can get the density of the object because the density of iron is the mass of iron divided by the volume. And, you know, this is the object that I'm talking about. Okay, so the density of iron, mass of iron divided by the volume of iron, which I called, you know, V of object. So I can get the volume of the object from this. I'm running out of space a little bit here, but the volume of the object, mass of the object divided by the density of the object, and I called it iron before, so I'll leave it the same. Okay, so again, we know M, we know G, minus density of fluid, which is given, volume of fluid. So my notation's not the best here. This is the density of the fluid, so this is the density of H2O. I don't want to confuse you with calling it F. This is Fe for iron. This is the density of the fluid, which is H2O. This is the volume of the fluid. Again, it's the same thing as the volume of the object, and then times G. Okay, so look back at that homework question. It's really the identical problem for that homework question. So you'll see something like this, some buoyant force problem. Okay, good. Okay, next we have a torque problem. An athlete holds a 7.5 kilogram shot put in his hand. So mass of the shot put, 7.5 kilograms. With his lower arm horizontal as shown in the picture. His lower arm has a mass of 2.8, so mass of the arm, 2.8 kilograms. And its center of gravity is 12 centimeters from the elbow. Okay, good. So here's the elbow joint. The center of gravity is 12 centimeters over, so you can assume that all of the mass of the arm is here. So that would be mass of the arm times g. And again, that distance is 12 centimeters. Excellent. How much force must the extensor muscle, which is labeled FM here, in the upper arm exert on the lower arm? So we want to know how much is this force. So extended free body diagram would be something like this. I'm just going to draw it kind of like a plank. So there's the pivot point. Here's F muscle over here. And then we have mass of the arm times G. And then we have mass of the shot put times G. And all these distances we know, this one is 2.5 centimeters. I don't have room to write the units, but it's centimeters. This is given as 12 centimeters from the pivot point. And finally, in the picture, this is 30 centimeters. Okay. So all these torques are balanced. The torque by the muscle is making it rotate this direction counterclockwise. The torque by the arm is making it go the other way, and the torque by the shot put is making it go the other way. And they're balanced because it's not going anywhere. So this one would be force muscle, and it's perpendicular to the arm here, times 2.5, and that's all these are going to be in centimeters. I'm just keeping that in mind. Force from the arm would be the weight of the arm, and then that distance is 12 centimeters. And then plus mass of the shot put times g, that's the force of the shot put, and then the distance would be 30 centimeters. Centimeters, centimeters, centimeters in all the terms, so the centimeters actually cancel out. If you want to convert these to meters, that's fine too, but in this problem it's okay that I don't, because each of these has a centimeter, and again that cancels out. And then the only thing that you don't know is the force by the muscle. So do a little bit of algebra. I'll just put ... force of muscle equal to. Okay, so you'll definitely see a balancing force and torque problem. The one that comes to mind is, go through this one, make sure you can do this one. But what if you had something like this? And this is a homework problem. What if you had a beam attached by a cable at some kind of angle here? This was one of the homework questions. So the beam itself has weight right in the center. You had tension this way. So if you know M and G, how much is the tension going to be? So take a look back at that one, hint, hint, on that homework as well. Okay, balancing torques. Okay, moving on to number 8 then. Find the first 3 harmonics of a string of linear mass density 2 grams, so that's what mu is, 2 times 10 to the minus 3rd kilograms, though, per meter, to put it in the correct units. Find the first 3 harmonics of a string, this linear mass density, length of 0.6 meters, and the tension is given, so force of tension, 50 newtons. And we want to find the first 3 harmonics. Okay, so remember, wave speed is the square root of the tension divided by the mass per length, but it's also equal to the frequency times the wavelength. So in this one we're not really asked about the speed, but I'm just giving you more information. So frequency times wavelength, square root of tension over mu. Good, so let's see, we know the tension, we know mu, we're trying to figure out the frequency. Okay, so the frequency would be equal to 1 over the wavelength times the square root of tension over mu. The thing is, we can get the frequency if we knew the wavelength. And we can get the wavelength. So for the first harmonic, the wavelength would be 2L over m. And, that's where m is equal to 1. So wavelength 1 would just be equal to 2L. So 1.2 meters. So you could use that to get the fundamental frequency then. So use this as the wavelength. So the fundamental frequency would be 1 over the wavelength associated with the first harmonic, and then tension times mu. So get that one, and then the second harmonic would be twice the first harmonic. The third harmonic is 3 times the first harmonic. You can see all these follow that pattern. If this is the fundamental, this is twice as big. This is 3 times as big as the fundamental, and similarly for the rest of them. So really, once you get the first harmonic from this equation, the other ones are just multiples of that. Okay, so keep in mind this relationship here. You'll definitely see something like that. And don't forget how the wavelength is related to the actual length of the string. Okay. Another fluids problem. The Aswan High Dam on the Nile River is 111 meters high. Okay, so the height of this 111 meters. What is the gauge pressure in the water at the foot of the dam? Okay, so here's the relationship between pressure and depth. So we've got the pressure at the top here, which is open to the atmosphere, 1.013 times 10 to the 5th, pascals. That's what 1 atmosphere is. And then we have got depth down here, and this distance is h. So the pressure at the bottom is greater than the pressure at the top because there's a whole column of fluid here. So we've saw this before, like P1 would be equal to P0, which is at the top, plus rho g h. So gauge pressure, that's what it's asked for here, gauge pressure just refers to the amount of pressure in addition to atmospheric pressure. So when manufacturers make the gauges, if you just look at it, you're walking around with a pressure gauge, it says 0. It's already taking into account atmospheric pressure. So we don't want atmospheric pressure involved, we just want the additional amount. So you say you have this gauge somewhere over here, it doesn't read anything, it reads 0, it's already taking into account the atmosphere. Now when you take it down here and put it here, you just want to measure the pressure due to rho GH. So that's what it's asked for here. Density times G times H, that's the gauge pressure. The density is given because it's water. We have 9.8, and then we have the height, which is actually given as well. We did some problems like the deepest part of the ocean, things like that, in the homework. So you'll definitely see something like this, a pressure at depth problem, so be ready for that. Chapter 10, number 10, another fluids problem. Ideal incompressible fluid flows in a horizontal pipe. If the pipe widens to twice its original radius, what is the flow in the wider section? So something like this. So we have some speed here, 12 meters per second, and maybe we can call this side radius 1. The pipe widens to twice its original radius, so radius 2 over here, and we know it's twice radius 1. Okay, so that's the speed in this part. Here's the speed over here. That's what we're trying to figure out. So this is kind of a problem where you know the speed here. When it widens to twice its radius, it's going to slow down. So if the pipe is twice as big in radius, does that mean the speed is half as much? Well, it turns out no, it doesn't. And this is the reason why. We have volume flow rate. So V1 times area 1. The amount of volume flowing through the pipe here has got to be the same as the volume flowing through here, and that's what volume flow rate is. So Q in this context is volume flow rate. So how does it relate to the radius? So I'm assuming it's this shape. This would be pi r1 squared. That's the cross-sectional area, and that would give us V2 pi r2 squared, and then the pi's cancel out. So V1 R1 squared is equal to V2 R2 squared. So we see we've got the square root relationship. So let's solve for V2, and you'll see what we get here. So V1 R1 squared over R2 squared is equal to V2. The problem seems to be that we don't actually know what R1 is, but we don't need to know what it is. It's going to cancel out. So we've got V1 R1 squared, and then R2 squared, but R2 is equal to 2R1, and then don't forget to square it. And then finally, V1, this would be an R1 squared and R1 squared, they cancel out, and you're left with 1 over 4. Right, you see the R1 and the R1, they're both squared, they cancel out, and then you have a 2 squared, which is a 4. So if you make the pipe radius twice as big, the speed's going to be 1/4 as much because of this squared relationship here. Okay, so you'll see something like this on the test as well, a volume flow rate problem. Okay, number 11. A child is riding a merry-go-round at 7.1 RPM, so that's sort of like a frequency, but it's just not in SI units. If the child is standing 4.65 meters from the center, how fast is the child moving? Okay, so here we have the picture. We sort of know the frequency, just not in SI units. So 7.18 revolutions per minute. We really need this to be revolutions per second for it to be frequency in SI units. The child standing 4.65 from the center, so the radius here, 4.65 meters. There's several ways of doing this problem, by the way. I mean, if you know the radius, you know you can figure out the distance around. From this frequency, you can figure out how long it takes to go around, and then from that, you can get the speed. Or if you want, we could use this relationship. R times omega is the speed, and that would be R times 2 pi F. Because remember, omega is 2 pi times the frequency. So we know R, it's given in the problem. We sort of have the frequency, but just not in correct units. If you use this for the frequency, you would get per minute instead of per second. So we have 1 minute, 60 seconds. And then we have a true frequency, and you can get the speed then, because now you know the frequency. So R is given, 2 pi, you know that, and then the frequency, just put it into SI units. Okay, good. So good. So this is V is equal to R omega. This is what I've done solves this problem. I'm just giving you a little bit more information. So say you're here compared to over here. So this person goes around once, this person goes around once. Both of these people, let's say this is position A and position B, they both go around 1 revolution in the same amount of time. So omega A is equal to omega B, right? They each go around 1 revolution in the same amount of time. So those are the same. What's different is the linear speed. Whoever's out here at position B has a greater linear speed than the person at A. So know that there's something similar to this question on the test dealing with this idea as well. Okay. Number 12, in simple harmonic motion. Okay, so immediately we know a lot. It's simple harmonic motion. We can figure out a lot about that. Let me just give you a refresher. So say you take a spring, a mass on a spring, which that's the part that we dealt with. You stretch it out to here. This is called the amplitude. And you let it go. It's going to go back through equilibrium, go over here. This distance, it's the same magnitude of distance. Okay, so we know a few things about it. Here is the maximum speed. Here's where the speed is equal to 0. Same thing over here. Speed is equal to 0. This is where all of the energy is spring potential energy. Same thing over here. All of the energy is spring potential energy. Here, all of the energy is kinetic energy because it doesn't have any spring potential when x is equal to 0. Okay, so maximum speed, no speed. This is like where all the energy is spring potential energy, because that's what this is. I'll write it over here just to remind you. That's all the energy spring potential. All of this energy there is spring potential. All of the energy here is kinetic. So that's where the kinetic energy is the maximum. Okay, so let's see what we can make with this one. Simple harmonic motion, when is the speed the greatest? Okay, the speed is the greatest when we pass through equilibrium. That's when the kinetic energy is a maximum. That's when the spring potential energy is 0. So maybe I could actually put this here. Kinetic energy 0, kinetic energy 0, spring potential energy 0 at the center point. Okay. When's the speed the greatest? When the magnitude of the acceleration is a maximum. Okay, so let me add acceleration here. So this is where the acceleration is a maximum. The magnitude of it is a maximum. Here's where the acceleration is a maximum as well, over here. Here, right, going back through the equilibrium position, so that's where all this is, I'm writing this for, the equilibrium position right here. This is where the acceleration is equal to 0. The spring's not stretched or compressed at that point. Okay. So it's not this one because that's where the acceleration will be 0. Where the potential energy is a maximum, well, no. Where the speed's the greatest, the spring potential energy is actually 0. When the potential energy is 0, okay, that works. And it says there could be more than one. When the displacement is a maximum, so that's not true. The displacement's a maximum here and here. That's where it's actually not moving for an instant. When the magnitude of the acceleration is a minimum. So that one's a little tricky. And it says the thing to read about it is magnitude of the acceleration is a minimum. So that's true. The magnitude is 0. Everywhere else the magnitude is actually a positive number. So the magnitude here is going to be a minimum because it's actually 0. So that one would actually work as well. Now, as far as usually this would say explain, so you can get partial credit. I mean, a nice little picture like this, and then a few sentences, confirming this. Like, for example, the potential energy is 0. That's where it's at. X is equal to 0. So all the energy is kinetic. Therefore, it's got to be moving the fastest. And same kind of idea for E. On the actual test, I won't have there could be more than one correct choice. I'll just have there being just one correct choice, so you don't have to, try to figure out how many of them are right. There'll just be one that's correct. Okay, great. A couple more to go here. A uniform solid cylinder, mass 10 kilograms, can rotate about a frictionless axle through the center. Okay, good. As shown. A rope wrapped around the outer radius, so radius 1 is 1 meter, exerts a magnitude of force of 5 newtons, so that's this one here. Okay, excellent. A rope wrapped around the outer one, okay. Second rope wrapped around another section where the radius is half as much, so 0.5 meters, exerts a force of 6 newtons. Okay, good. And then what is the angular acceleration of the cylinder? So it's a uniform solid cylinder. Okay, so what we know is the net torque is equal to I times alpha. So this is the rotational version of Newton's second law. So Newton's second law is F is equal to ma. Here we have torque is equal to I alpha. So instead of it being force, it's force, but where's the force applied? Instead of it just being m, it's m times, some factor of the radius squared. But that just depends on what shape we have here. And then alpha plays the role of regular acceleration. So these always take a little bit more work. So solid cylinder, we have 1/2 mr squared. And you don't have to write down all the rotational inertias of different shapes. I'll give that to you. So you can get rotational inertia from this. So we're given the mass. The radius I want to use is this bigger radius. It's the radius of the whole shape. So let me just call it, I'll leave it the same. Here's the shape. How big is the shape? Well, let's call it R1 there. Okay, so you can solve for this. It's going to take a little bit of plugging in to get the number there. Now the net torque, we have this force making it rotate to the right, or clockwise. F2 here would be making it rotate counterclockwise. Okay, so let's take this a step further then. The net torque is equal to I alpha, and then we have to supply the actual force and distances here. So I would have F2, where it's acting, R2, leave it the same, big R2, minus F1, the distance to the point where it's acting, R1. So then, this is the torque because of force 2, making it go counterclockwise. This is the torque because of force 1, make it go clockwise. Now I did this one minus that one because technically, if it's going counterclockwise, the torque is positive. Going clockwise, the torque is negative. Okay, so we're almost there. Then alpha would be F2 R2 minus F1 R1 divided by the rotational inertia. I just want to do one more step here just to look at the sign of this thing. So force 2, this would be 6 newtons times 0.5 minus 5 newtons times 1. And then divided by 1/2 mr1 squared. So this would be 1/2 10 kilograms, 1 meter, and don't forget to square it. So this would be 5 kilogram meter squared. If I did the math right, I think that's good. So if you notice, this is actually going to come out to be negative. let's see, we'll have 3 Newton meters minus 5 Newton meters divided by 5 kilogram meters squared. So that's minus 2 over 5. So really this should be minus 0.4 radians per second squared. Really up here it should say what is the magnitude of the angular acceleration, because technically it should be negative. It's going to accelerate counterclockwise. Okay, the last one then, number 14. So 14 questions on the practice test, 14 questions on the actual test. The density of material at the center of a neutron star is something like 1 times 10 to the 18th, so a billion kilograms per cubic meter. What is the mass of a cube? So how much is the mass of a cube of this material that is 1.76 microns, so to the minus 6 meters on each side. So that's just the side. It's a cube of material. And this side here is d. So the volume is just going to be d cubed. Okay, so the density is the mass divided by the volume. So the density times the volume will give us the mass. Okay, so again, density is given. The volume, you just have to do a little bit of calculating. It's a cube, you know, one side, so cube that. Multiply the density times the volume, you'll get the mass. Good, so number 14 wasn't the hardest question on the test, but you'll see something like this, maybe a little simpler, just, you know, density, mass, volume type problem. All right, good. So 14 questions. What I would do again is go through the practice test, go back through the homeworks, at least read the summaries of the chapters. If you don't have time, it's best to skim through the chapters and then go back through through the videos if you have time to watch those as well. Okay, great. Any questions, please email me, and I'll talk to you later. Bye-bye.